So, we start discussing the space group PMCN as we concluded in the previous section, that we have now an enough knowledge of the way in which the diagram which is consisting of symmetry elements appear, and also the diagram which consists of equivalent points appear. We also discussed the fact that in an orthorhombic system A, B, C can be interchanged. So, depending upon that, the corresponding symbols associated with the point group symmetry will also change. And therefore, even though this point group symmetry is here 2 by m, 2 by m, 2 by m, the order in which they come can be not exactly the way in which it is written in the international tables. So, this particular space group, if one searches in the international tables, you will not find. However, this is the space group in which the structure of calcium carbonate is reported earlier on, and that is why I thought that I will take this as an example. The other issue is that we are now in a situation to appreciate the structural aspects associated with the space groups. See, we know that we have been discussing that with respect to objects like here. But instead of objects, now we have realistic atoms which are connected to each other to form a molecule, or a compound which is represented in the unit cell, and so on. So, since we have come to that kind of a situation, we will now take an example of the structure of calcium carbonate, and it is reported in literature in the space group PMCN. So, we will take into account the space group PMCN. You are all familiar now with the way in which PMCM develops and the way in which the positions of the individual symmetry operations appear in this space group. We know that once there is a primitive lattice, the number of lattice points is 1. The mirror symmetry is now perpendicular to the A axis. You see that this is the mirror and it is perpendicular to the A axis. Remember, this is 2 by m, 2 by c, 2 by n, and with our knowledge on the way in which the symmetry element moves away from the origin when we have a translation involved symmetry operations, this actually now represents the mirror at 1/4 along the A direction. So, it moves 1/4 perpendicular, this is the A direction, it moves this is the A direction, sorry, it goes to 1/4 and then it is normal to the A direction. So, the mirror plane is normal to the A direction and it is removed by 1/4 in this direction. Now, if we take the C glide into account, that again moves by 1/4 and this moves now in a direction which is perpendicular to this. We also invoke the presence of additional 2-1 screw axis, as we discussed in the case of PBCA. Additional 2-1 screw axis will develop at various places along the 3 directions. The fact that this is a centrosymmetric system, we now put the center of symmetry at the origin. The moment the system is centrosymmetric, we have to put this symmetry center of symmetry at the origin. So, 0 0 0 therefore is up here, and this is the A direction, this is the B direction, and we have now a mirror plane which is removed by 1/4 and is normal to the A direction. A C glide removed by 1/4 and is normal to the B direction. And the appearance of the N glide is shown up here because it occurs in the 3rd dimension, and therefore, it is shown with a typical symbol which represents the glide plane, and this arrow which is coming in the diagonal says that it is the N glide. So, we therefore have the full representation of the mirror, the C glide and the N glide in this symmetry diagram. So, this is a complete symmetry diagram representing the PMCN. The way in which the equivalent points develop as a consequence are shown here, and we will have to refer to the next slide to understand what these positions are. For example, there are 8 possible symmetry positions in the unit cell in the general position, the point symmetry being 1, and those 8 positions are given here. Since the crystal system is centrosymmetric, we have plus xyz and also minus x minus y minus z. So, xyz and x bar, y bar, z bar, which are now indicated here. Now, the presence of the mirror plane, which is now at 1/4, will generate, the mirror plane is going up here now. And since the mirror plane is going down here in this direction, we see that there is a mirror relationship between these two objects, and so also the mirror relationship between these two objects, which are generated due to the presence of the center of symmetry which exists here. So, we see that also the presence of the n glide and the c glide will introduce these two additional symmetry elements. So, overall we get a mirror symmetry at this position and a c glide at that position, and so the total number of equivalent points after transforming from outside of the unit cell to the inside will give rise to 8 of them. I want you to learn and work out how these equivalent points come based on the table which is given up here. I do not think we have time to discuss that again and again. We have already seen the orthorhombic symmetry, we have seen PMC21, we have seen PBCA, and we have of course very clearly seen 2 1 2 1 2 1. So, we have a knowledge of how these equivalent points get generated, and since the coordinates are given here, find out where these coordinates are with respect to the diagram which is shown here. Then you will be convinced that there are 8 equivalent positions corresponding to these 8 general positions. Now, it so happens that in this space group, because of the additional possibility of the object having a mirror symmetry or a 1 bar symmetry, that is the center of symmetry, or a 1 bar symmetry, which is again a center of symmetry, we get special positions. We are quite aware of how the special positions develop. So, I will not spend time again on this one, except to tell you that there are 3 possible positions which all generate 4 multiplicity. So, z is equal to 4, which means that in fact we will have only half the molecule allowed with respect to the general 8 positions. So, these therefore define now the mirror position, the 1 bar position and 1 bar position, and the total number of equivalent points are 8. Now, we come to a situation where we look at the realistic situation. So, we are now going to take the structure of calcium carbonate. There are various ways in which calcium carbonate crystallizes, and one of the ways in which it crystallizes is referred to as the mineral phase, which is called aragonite. So, this is a naturally occurring mineral, this mineral aragonite, and the structure of this goes into the space group PMCN. The crystal structure has been determined, single crystals of aragonite have been grown in the laboratory, the structure has been determined. Now, once the structure has been determined, we get to know the total number of calcium carbonates that are present inside the unit cell, depending upon the volume of the unit cell and other factors, which I will discuss in a minute. These give us rise to 4 calcium carbonate units. So, Z is equal to 4. So, there are 4 calcium carbonates units inside the unit cell. That means the unit cell can accommodate 8 equivalent positions, but it can have only 4 calciums. So, since it can have only 4 calciums, the calcium atoms can be associated with a mirror point symmetry or a 1 bar point symmetry, which is with 0 0 0, or the other 1 bar point symmetry, which is with 0 half 0, because all these 3 possibilities can be taken into account, and calcium can have a choice where it wants to sit. See, this is how the structures develop. You see, calcium carbonate, we already know, has certain restrictions from the way in which it forms the structure. The calcium coordination site is the one which decides how the coordination around calcium should develop in the crystal structure. So, the calcium, therefore, since there are only 4 calciums, these 4 calciums can go to M or 1 bar or 1 bar. It can take any one of these. And same is the story with the carbon. There are 4 carbon atoms. On the other hand, there are 4 times 3, there are 12 oxygen atoms. So, these oxygen atoms have a very clear liberty of how they could arrange in generating the calcium coordination, because these 12 can be, say 8 of them can be sitting in general position and 4 can be in any of these 3 special positions. That is one option. The other option is 3 types of oxygen sit in each of these 1 bar and M positions. that will also total up to 12. So, now is a situation where we have a unit cell which is PMCN, into which the crystal structure has gone into. Calcium carbonate has gone into that structure, generating the mineral aragonite, which is a naturally occurring mineral. So, when the naturally occurring mineral formed, these were the options that were given for the compound to form. Calcium, carbon and oxygen, these were the options which were given for this thing to form. So, calcium therefore can have 4, that can be 4 calciums, 4 carbons and 12 oxygens, and as we discussed, the distribution among the various types of symmetry elements in the unit cell is possible. Now, how do we find out how many molecules are there in the unit cell? That is done by using this formula Nm equals N rho V. This formula Nm equals N rho V. Let me explain this formula in a little more detail. N is the total number of molecules in the unit cell, which could be the Z value. M is the molecular weight associated with the compound. Since we know what compound is crystallizing, we can have the identification of the molecular weight. We can determine the molecular weight of calcium carbonate by knowing the atomic weight of each one of these atoms and adding them up into the compound. So, we have the molecular weight. We can also determine the molecular weight of this particular crystal using mass spec. So, we will have a measure of the molecular. So, experimentally or theoretically we can simply calculate by using the atomic masses. So, we know the molecular weight of the system. N is the Avogadro number. The Avogadro number is 6.023 into 10 to the power of 23, as most of you know, per mole, and that Avogadro number is a constant and it can fix the molecules inside the unit cell. So, N is the Avogadro number. Rho is the density of the crystal. We will talk about the density of the crystal in a little while. Rho is the density of the crystal and V is the volume of the unit cell. So, in this particular case, once we know the value of A, B and C, this is an orthorhombic system, because the crystal system, as you see, is PMCN. Crystal system is PMCN. So, it is an orthorhombic system. In the orthorhombic system, the volume will be A times B times C, the product of the 3 A, B and C, and therefore, V is equal to A dot B cross C. We can calculate the volume. So, once we have this volume available to us, which is from the experiment which has been determined to using X-ray diffraction to show that there are 4 molecules in the unit cell. How do we find out that there are 4 molecules in the unit cell is what we are discussing now. So, we first determine the cell dimensions. We determine the value of A, B, C, alpha, beta, gamma. We identify the space group and this has been identified as PMCN. Then we go ahead and calculate the volume of the unit cell. So, we have volume known in this expression. We know the volume, we know the Avogadro number, we know the molecular weight. The 2 unknowns are the number of molecules in the unit cell and the density associated with the crystal. The density associated with the crystal can be measured. In earlier days, as I mentioned in the previous previous class, that we were asked to determine the density whenever we do any crystal structure determination. It was a compulsory requirement, but now people do not bother about it and they simply get whatever density the software gives, they assume that is the density of the crystal. There is always a possibility of going wrong in this assumption, because the software gives the density of the crystal based on the value of m. And suppose, let us say in this example n was assumed to be 8, then we will get a wrong density, because we know that n is equal to 4 by eventual determination of the density. So, how one determines the density of a crystal? The density of a crystal is determined based on an experiment which is known as the flotation experiment. It is basically the principle of Archimedes. You know the principle of Archimedes, that when an object is immersed inside a solution, the weight of the object equivalent will be taken out from the liquid. So, it will be displaced from the liquid. So, the volume of the liquid is equivalent to the weight of the sample which is inside. So, if a person gets into the bathtub as Archimedes did, certain amount of water flew from the bathtub, and that is how the Archimedes principle came up, as you all know. So, similar thing we assume here. So, what we do is we roughly take two liquids, one with a lower density and another with a higher density. And these two liquids, these two solvents for example, these two solvents could have a property that this compound calcium carbonate will not dissolve in them. So, for example, in this case we cannot take water, it will dissolve in water. So, we have to take two solvents. Let us say we take alcohol on one hand and then some higher density liquid which could be methylene bromide or methylene iodide or something like that. These solvents are chosen in such a way that calcium carbonate will not dissolve in them. We already know the densities of these two liquids from literature. So, we take the value of the literature for these two liquids and then we drop the crystal. One single crystal of calcium carbonate is taken and is dropped inside the liquid with one of the solvents. Let us say we take the solvent which has lower density and then we drop the crystal inside the solution which has lower density than the anticipated density of the crystal. Then what will happen? If you have a lower density and you drop the higher density crystal on top of a lower dense liquid, what will happen? Will it sink or will it float? What will happen? The density of the liquid is lower. So, will it sink or will it float? It will sink. So, if the density is higher, it will float. So, we take the mixture of these two, nicely mix them up and then put the crystal and adjust the ratios of these solvents such that there will be one stage we can visibly see the crystal in between the two, that means going at the middle. So, we have these two solutions mixed. So, this crystal will float in the middle. This is known as the flotation technique for determining the density. Then we take that mixed liquid and then measure the density of that using a densitometer. We can either use a densitometer or use a specific gravity bottle and then use the density determination methodology, which is very well known from high school. So, we determine the density of the crystal. So, that means we have the knowledge of n, we know what n is, what rho is and what V is. Rho is expressed in grams per cc or kilograms per meter cube. Then m is the molecular weight of the material and so we know now V, rho, n and m, we should be able to determine n. And this is the way in which it has been identified that there are 4 of calcium carbonate units inside this PMCN units n. So, to repeat the whole thing once very quickly, we have the material calcium carbonate, the aragonite form that has been crystallized. The crystals have been subjected to X-ray diffraction and the unit cell dimensions have been determined by some technique which we are going to learn in the future. So, we determine the value of A, B, C, alpha, beta, gamma. The value of A, B, C, alpha, beta, gamma tells us that it is an orthorhombic system. We go further and determine the symmetry that is associated with this orthorhombic crystal and we find it is PMCN. The moment we know it is PMCN, we know that this is orthorhombic number 1 and number 2 there are 8 general positions and 4 special positions as indicated here. There are 8 general positions, 4 special positions corresponding to a mirror symmetry, a 1 bar symmetry and a 1 bar symmetry. Then based on the knowledge of the density which has been measured using this methodology we just described, we know the volume, we know the density and we know the Avogadro number. The right hand side is evaluated and is divided by the value of m, which is the molecular weight, and that value will give us the value of n, and it turns out to be the value of n is 4. That means we have 4 calcium carbonate units in this unit cell. So, that knowledge is gained. Now, we will see when we actually determine the structure, what kind of positions calcium took, what kind of position carbon took and what are the positions oxygen took. As we already discussed, there are only 4 calcium atoms. So, obviously, these 4 calcium atoms should sit in one of the special positions, because 8 positions cannot be generated for 4 calciums. There are only 4 calciums. Well, it can be generated with half occupancies and so on, but that is unlikely in a very nicely determined structure. So, in an ordered calcium carbonate structure like that found in the aragonite mineral, we will have 4 calcium atoms. So, they have to sit in one of these special positions. And the carbon atoms also should sit in one of these allowed special positions. Oxygen atom, as we discussed again, that 4 times 3 is 12. So, it can sit 8 of them in general position and 4 in one of these special positions, or all 3 oxygens can be distributed in these 3 special positions as summing up to 12. So, 4, 4, 4, that will make it 12. So, these are the possibilities. Now, this is decided by the nature of the structure, the coordination around calcium, the way in which the carbonate units join together and so on. The bonding comes into the picture here. The nature of the bonding, the nature of the coordination site around calcium will now tell us how these calcium, carbon and oxygen go into this particular space group, occupying the special positions or the general positions as we have discussed. So, here is a situation where we have now landed ourselves into that whenever some crystallization takes place of a material or a compound, the compound can go in and behave in such a way that the individual elements now constituting the compound can follow the required multiplicity and the special point symmetry and so on, and therefore, their coordinates are kind of predetermined once they go into the space group. So, the symmetry therefore is the key factor here. It drives the elements in this particular compound to go into their respective positions. So, we have seen that this is a PMC and space group. So, there are 8 equivalent points, but when they are in special positions it becomes 4, and therefore, we have the possibility that 4 calciums and 4 carbons will sit only in special positions, whereas oxygen has the freedom to go either there or sit only here. And let us now look at the solved crystal structure, because we now have an information that N is definitely 4 from this expression. And so, this is a universal expression. This can be used for any crystalline material. Then once we determine the density, once we determine the unit cell dimensions and volume, and if we know the molecular weight, we can calculate the number possible in the unit cell. Suppose we are looking at a structure whose molecular weight is not known, and it goes into a space group where N is fixed, the number of molecules in the unit cell is fixed. This is probably a very good method to determine molecular weight very accurately. Nobody uses this method, but one can determine the molecular weight of a given compound by using this formula, and this determination of the molecular weight will be extremely accurate, because we have the A, B, C, alpha, beta, gamma determined at angstrom level. So, the accuracy associated with this molecular weight determination will be very, very reliable. But this method is quite expensive to do, because we have to, number 1, grow the crystals, number 2, determine the volume by X-ray diffraction experiments, determine the density by flotation, and then calculate the M value. So, it is going to be a tedious one. Instead, one can use the routine methodology that is available for molecular weight determination. But if the compound is unknown, this is the question which we will come again later as we go to the structure determination part. If the compound is unknown, we do not know whether this crystal which I have in my hand is calcium carbonate or not. Is there a way I can find out that it is calcium carbonate? And that is your approach. Eventually, we want to get to the structure determination protocols to determine where the atoms are and what those atoms are, and in what way they decide to sit inside the unit cell. So, in principle, we have come to the level of first level understanding of how this compound could be. So, suppose you are given an unknown compound and you are asked to crystallize, you crystallize the compound, but you do not know what are the atoms inside that, let us say. You only go to the X-ray diffraction machine and then characterize the unit cell dimensions. And let us say the scattering is very good, the crystal quality is very good, you get a volume. So, you use this volume information, you know the Avogadro number, and since there is a good crystal that is formed, you can also determine the density. So, the right hand side is available to you for any compound, and the left hand side the right hand side will also tell you what are the various possible general positions with which we can associate this compound to, and therefore, we know roughly what should be the N value or the Z value if all the atoms in this structure are sitting in general positions. Of course, if they are sitting in special positions, also we know the distribution that is possible. So, in principle, we should be able to determine the molecular weight, and in the long run, in principle, we should be able to identify which atom is which by looking at the scattering characteristics, the details of the intensity analysis and so on. So, the take home from this discussion, a long discussion rather, is to say that even if you do not know anything about the structure, if for example, the chemist told you that this is the possible formula and he may be totally wrong, it does not matter to the X-ray structure specialist, so much that once Jack Dunitz made a comment, who is one of the top crystallographers of the world. He made a comment that a chemist keeps his compound in a dark room, he gropes in the dark, he makes the compound and gropes in the dark. So, it could be any of these structures. So, he uses various spectroscopic methods, some other methods to sort of a priori predict what could be the structure. But this is like entering a dark room and trying to, let us say, find this monitor inside the dark room. Suppose everything is dark here and we enter the room and we want to find where this is, it is going to be difficult. So, what crystallography does, what crystal structure determination protocol does, in fact, in general what crystallographers do is to come and switch on the light. So, the moment we switch on the light, we know where the object is, where the crystal is, where the atoms are going into the various parts of the unit cell and so on. So, a chemist gropes in the dark and the crystallographer gets in and puts on the light in that particular room to find the object. So, thereby the determination of the crystal structure by X-ray diffraction is unambiguous. Once you do a thorough job of analyzing the X-ray structure, then whatever you have determined is going to be the final structure in the solid state. See, once you dissolve the crystal or allow the crystal to become a liquid and liquid becomes gas and so on, it is not guaranteed that the structure which is in the solid state will be maintained. Because as you all know, the structure in the solid state is such that the molecules are connected to each other by various intermolecular interactions. And these intermolecular interactions could be strong, they can be weak, depending upon the situation. The molecules arrange themselves to go into a given space group. As we discussed the other day, the possibility of polymorphism. They can go into different space groups. When they go into different space groups, different types of intermolecular interactions will hold the molecule together. And as a result, once we disturb these intermolecular interactions, we do not know what kind of reorientations occur in the molecule. To a very large extent, most of the structures remain unaltered, which is because of the fact that they are all bound by very strong covalent ionic, that kind of bonds, which are strong bonds. So, energetically it is very difficult to disturb the molecule just by removing the intermolecular interactions. But then there are possibilities, particularly in organic systems and so on, where there is a potential for intramolecular interactions to develop in lieu of the intermolecular interactions. Then you have a possibility that conformations may change. So, the conformation you may get from NMR may not agree with the conformation you got from the crystal structure. This is particularly true with small molecules. The story with large molecules, particularly proteins and viruses and so on, is very interesting, because these molecules, they do not crystallize with the intention of having only the molecular species. They always crystallize with a large amount of what we call as solvent water, and there is a lot of water around it. So, more or less the crystal structure, if we determine the crystal structure of a protein, it mimics the actual structure of the protein in the biological media, and that is a very big advantage as far as protein structure determination is concerned. The protein structure also has a issue that it depends upon the various states of solvation. So, you can have polymorphism in proteins as well, depending upon the nature of the solvation dynamics which occurs around the protein molecule and the way in which the solvent structure develops around the protein molecule. Now, why are we discussing all these issues? We are discussing all these issues to bring home the importance of understanding where the atoms are and how the atoms now are distributed inside the unit cell. So, if we consider therefore the case of this calcium carbonate, it crystallizes in a PMCN space group. The options that are given to the atoms have already been discussed. So, now we have to see how the atoms are located. The moment we know how the atoms are located, we will know about the geometry of that particular molecule as well. So, all these issues will come up if we go to the next slide. and that particular slide will tell you how the atoms in calcium carbonate are actually located inside the unit cell, and we will discuss that in a little more detail. But at this particular moment we see that there are 4 calcium carbonate atoms in the unit cell based on the density, and the atomic coordinates are given in this table. The atomic coordinates tell us that calcium, there are 4 calcium atoms. The calcium atoms decide to sit in the mirror symmetry position, which is generating the special 4 positions, z equals 4, the z equals 4 generation position. So, we will have therefore 4 calcium atoms. Carbon also decides to use the mirror symmetry. It could have used mirror as well as 1 bar, but it uses the mirror symmetry. 4 of the oxygens use the mirror symmetry. So, this now determines the geometry of the calcium surroundings. And then we have of course the oxygen 2, the second one generally occupies all general positions. And at this stage we will discuss independently how we go about understanding this. Okay.